The role of nanotechnology, engineering at the atomic scale. Imagine building a machine so small that you could fit millions of them on the head of a pin. Picture assembling structures atom by atom, creating materials stronger than steel yet lighter than feathers, and engineering devices that can travel through your bloodstream to repair damage at the cellular level. This isn't science fiction, this is nanotechnology, and it's reshaping our world in ways that would have seemed impossible just decades ago. Welcome to this Duel of Concepts deep dive, where we'll explore how engineering at the atomic scale is revolutionizing everything from medicine to manufacturing, and why the smallest innovations are creating the biggest impacts. What is nanotechnology? To understand nanotechnology, we need to first grasp just how incredibly small we're talking. The prefix nano comes from the Greek word for dwarf, and in scientific terms, it represents 1/1,000,000th of a meter. To put this in perspective, a human hair is about 80,000 nanometers wide. A red blood cell measures roughly 7,000 nanometers across. We're operating at a scale where individual atoms and molecules become the building blocks of our creations. Nanotechnology is a science, engineering, and application of materials, devices, and systems at this nanoscale, typically ranging from 1 to 100 nanometers. At this scale, materials begin to exhibit unique properties that are fundamentally different from their bulk counterparts. The laws of physics that govern our everyday world start to bend and twist in fascinating ways. Quantum effects become dominant, surface area to volume ratios skyrocket, and materials can display properties that seem almost magical compared to their larger scale versions. The field emerged from the visionary thinking of physicist Richard Feynman, who in 1959 gave a famous lecture titled "There's Plenty of Room at the Bottom." He proposed that there was no fundamental physical law preventing us from manipulating individual atoms and molecules. What seemed like pure fantasy then has become today's cutting-edge reality. Historical development and key milestones. The journey from Feynman's theoretical musings to today's nanotechnology revolution spans over 6 decades of remarkable scientific achievement. In the 1970s and 1980s, researchers developed the crucial tools that made atomic scale manipulation possible. The scanning, tunneling microscope, invented in 1981, allowed scientists to not just see individual atoms but actually move them around, quite literally pushing atoms from place to place. The 1980s also saw the discovery of fullerenes, soccer ball-shaped carbon molecules that earned their discoverers the Nobel Prize. These structures, along with carbon nanotubes discovered in the early 1990s, demonstrated that materials engineered at the nanoscale could possess extraordinary properties. Carbon nanotubes, for instance, are stronger than steel yet incredibly lightweight and can conduct electricity better than copper. The real acceleration began in the 1990s with increased government funding and the establishment of dedicated nanotechnology research programs worldwide. The National Nanotechnology Initiative launched in the United States in 2000, committing billions of dollars to research and development. Similar programs emerged globally, creating an international race to harness the power of the very small. Key breakthroughs continued throughout the 2000s and 2010s. Researchers developed new synthesis methods, created novel nanomaterials, and began translating laboratory discoveries into commercial applications. The invention of graphene, a single layer of carbon atoms arranged in a honeycomb pattern, opened up entirely new possibilities for electronics, materials science, and energy storage, current applications and breakthrough technologies. Today, nanotechnology has moved far beyond laboratory curiosities to become a multi-billion-dollar industry. Why touching virtually every aspect of our lives in electronics? We're witnessing the continuation of Moore's law through nanoscale engineering. Computer processors now feature transistors that are just a few nanometers wide. The smartphone in your pocket contains billions of these nanoscale switches, each smaller than many viruses. In medicine, nanotechnology is creating revolutionary treatment approaches. Nanoparticles can be designed to target specific types of cancer cells, delivering chemotherapy drugs directly where they're needed while minimizing damage to healthy tissue. Researchers are developing nanorobots that could perform surgery at the cellular level, repairing damaged DNA or clearing arterial blockages from the inside. The materials science applications are equally impressive. Self-cleaning surfaces using titanium dioxide nanoparticles are already in commercial use, breaking down dirt and pollutants. When exposed to light, nanocomposite materials are making everything from tennis rackets to airplane wings stronger and lighter. Some textiles now incorporate silver nanoparticles for their antimicrobial properties, creating clothing that stays fresh longer. In energy, nanotechnology is driving improvements in solar cells, batteries, and fuel cells. Quantum dots, semiconductor nanoparticles, can be tuned to absorb specific wavelengths of light, potentially leading to solar panels that are both more efficient and less expensive than current technology. Nanomaterials in lithium-ion batteries are increasing energy density while reducing charging times. Environmental applications are equally promising. Nanomaterials can remove pollutants from water and air with unprecedented efficiency. Some nanoparticles can break down toxic chemicals into harmless components, while others can capture and concentrate valuable materials from waste streams. Advantages and revolutionary potential. The advantages of nanotechnology stem from the unique physics that govern matter at the nanoscale. When materials are reduced to nanometer dimensions, their surface area to volume ratio increases dramatically. This means a much larger proportion of atoms are at the surface where chemical reactions occur, making nanomaterials incredibly reactive and efficient. Quantum effects become significant at the nanoscale, allowing engineers to literally design materials with desired properties. By controlling the size, shape, and composition of nanoparticles, researchers can tune their optical, electrical, and magnetic properties with precision that was previously impossible. This level of control opens up possibilities that seem almost like alchemy, turning abundant materials into substances with properties rivaling or exceeding those of precious metals and rare elements. The precision possible with nanotechnology could revolutionize manufacturing. Instead of cutting, grinding, and shaping materials inherently wasteful processes, we could build products atom by atom, using only exactly what's needed. This bottom-up manufacturing approach could dramatically reduce waste and energy consumption while creating products with perfect internal structures. In medicine, the advantages are particularly compelling. Nanoparticles can be engineered to cross biological barriers that stop conventional drugs, potentially treating diseases that are currently incurable. The ability to operate at the same scale as biological molecules means nanotechnology could interface directly with the machinery of life, repairing, enhancing, or replacing biological systems with unprecedented precision. Challenges and limitations. Despite its tremendous promise, nanotechnology faces significant challenges that must be overcome for its full potential to be realized. Manufacturing at the nanoscale remains extraordinarily difficult and expensive. Creating large quantities of nanomaterials with consistent properties requires sophisticated equipment and precisely controlled conditions. Many nanomaterials that work beautifully in laboratory settings prove challenging to produce commercially. The toxicity and environmental impact of nanomaterials remain largely unknown. Because they behave so differently from bulk materials, we can't simply assume that nanomaterials will have the same safety profiles as their larger counterparts. Some studies suggest that certain nanoparticles could accumulate in organs or cross the blood-brain barrier, potentially causing unforeseen health effects. The same properties that make nanomaterials useful, their high reactivity and ability to penetrate biological barriers, could also make them dangerous. There are also fundamental physical limitations. As we approach atomic scales, quantum effects and thermal motion become increasingly important. At room temperature, atoms are constantly vibrating, which can disrupt the precise positioning required for some nanotechnology applications. Building stable, functional devices at these scales requires overcoming significant engineering challenges. Standardization and regulation present additional hurdles with such a rapidly evolving field. Establishing safety standards and regulatory frameworks is challenging. Different countries are taking varying approaches to nanotechnology regulation, potentially creating barriers to international development and commercialization. Future prospects and emerging trends. Looking toward the future, nanotechnology promises to become even more transformative as current limitations are overcome. Researchers are developing new manufacturing techniques that could make nanomaterial production faster, cheaper, and more scalable. Self-assembly approaches, where molecules spontaneously organize into desired structures, could revolutionize how we build nanoscale devices. Artificial intelligence is increasingly being integrated with nanotechnology research, helping scientists design new materials and predict their properties before they're actually created. Machine learning algorithms can analyze vast databases of material properties to suggest new combinations and structures that human researchers might never consider. The convergence of nanotechnology with other emerging fields is creating exciting new possibilities. Nanobiotechnology combines engineered nanomaterials with biological systems, potentially leading to hybrid devices that blur the line between living and artificial. Quantum nanotechnology could harness quantum effects for computing and sensing applications that are impossible with conventional technology. In medicine, the future could bring programmable nanomachines that patrol our bloodstreams, detecting and treating diseases before symptoms appear. These devices might communicate with each other and with external monitoring systems, creating a comprehensive health management network operating inside our bodies. Environmental applications could expand to include large-scale atmospheric engineering, with nanomaterials designed to capture carbon dioxide or break down atmospheric pollutants. Some researchers envision swarms of nanomachines that could clean up oil spills or toxic waste. Sites with unprecedented efficiency. Conclusion. As we've explored in this deep dive, nanotechnology represents one of the most significant technological frontiers of our time. By learning to engineer matter at the atomic scale, we're gaining unprecedented control over the materials and devices that shape our world, from revolutionary medical treatments to super-efficient solar cells, from self-cleaning surfaces to quantum computers. Nanotechnology is already transforming industries and improving lives. The challenges are real. Questions about safety, manufacturing scalability, and regulatory frameworks must be carefully addressed. But the potential benefits are so significant that research and development continue at a breakneck pace around the world. We're still in the early stages of the nanotechnology revolution, and the most exciting applications may still be ahead of us. What makes nanotechnology particularly fascinating is how it challenges our intuitions about how the world works at the nanoscale. The familiar rules of physics give way to quantum mechanics, and materials display properties that seem almost magical. Yet these aren't supernatural phenomena. They're the result of careful scientific understanding and engineering precision. As we stand on the brink of even greater breakthroughs, one thing is clear: the future will be built from the bottom up, atom by atom. With nanotechnology leading the way, the smallest scale of engineering is creating the largest impact on human civilization, proving that in science and technology, thinking small can lead to enormous achievements. If you found this exploration of nanotechnology as mind-bending as we did, show some atomic level appreciation by hitting that like button. After all, every click is made possible by nanoscale transistors. Don't forget to subscribe to Duel of Concepts for more deep dives into the technologies reshaping our world. And let us know in the comments, which nanotechnology application do you think will have the biggest impact on your daily life? We'd love to hear your thoughts on how the smallest innovations might create the largest changes in your world.
This isn't just content, it's a Duel of Concepts deep dive crisis. Hit like, subscribe immediately, and let your voice be heard below.